Hello there. My name is Shubodh Sai and today I will be presenting our paper named LIP-Loc, LiDAR Image Pre-Training for Cross-Modal Localization. This research solves the problem of global visual localization in LiDAR maps. We first describe the problem statement of cross-modal global localization. Given a 2D RGB image as query, we want to find the best matching 3D reference point cloud. As you can see in the figure, the best matching point cloud for our 2D query image is represented by green dot with corresponding LiDAR point cloud, whereas the red dots are the incorrect matches. We are also addressing the inverse problem, that is, given a 3D point cloud as query, finding the best matching 2D RGB image. Our research leverages the contrastive language image pre-training or CLIP approach, which has been instrumental in multimodal learning for the domains of 2D image and text. By employing contrastive symmetric laws with batch construction techniques, we have applied this method to bridge 2D image and 3D LiDAR data to learn a shared multimodal embedding space. Here are our main contributions. Our work is the first work to apply batch loss approach to the cross-modal setting of image LiDAR data. We also establish the first benchmark for cross-modal localization on the Kitty dataset. We show zero-shot transfer capabilities on standard autonomous driving datasets like Kitty and Kitty 360. Our method significantly outperforms state-of-the-art recall at 1 accuracy on the Kitty 360 dataset by 22.4%. We also demonstrate a zero-shot capabilities and we beat SOTA by 8% without even training on it. Now we discuss our methodology. Our model uses contrastive learning to jointly train two encoders. One processes 2D images and the other processes 3D LiDAR data. We first create a batch of n pairs, each consisting of an RGB image and a LiDAR sample as represented by I1 T1, I2 T2, I3 T3 and so on. Our objective is to correctly match each image with its corresponding LiDAR data from all possible pairings within this batch. In this way, the cosine similarity between n positive pairings is maximized, whereas that between the remaining negatives pairings is minimized. So here I1 T1, I2 T2, I3 T3 and so on till IN Tn are the positive pairings, whereas the remaining pairs such as I1 T2, I2 T3 and so on, rest of them are negative pairings. Finally, over the obtained similarity scores, a symmetric cross entropy loss is optimized. The inference procedure is explained as follows. Given an RGB image, we pass it through its corresponding encoder to extract the embedding. For reference 3D LiDAR point clouds, we first convert it to range images, then we extract the corresponding LiDAR embeddings. Then the reference with the highest similarity score to the query is selected as the final prediction. The pose of this reference is extracted for the final global localization problem. We now discuss our results when tested on the KT360 dataset. Our approach, LIP-Loc, significantly outperforms the previous state-of-the-art method known as AECM-Loc on the KT360 dataset. Unlike AECM-Loc, which relies on fisheye images that require complex processing due to distortion and uses a specialized architecture, our method employs perspective image with a simple ResNet VAT architecture trained in contrastive loss format. This choice simplifies the process while also maintaining high accuracy. In the 2D 3D setting that you're seeing here, LIP-Loc significantly beats the baseline by 22% for recall at 1, and in the zero shot setting it beats it by almost 8%. And when we look at recall at 20, Accuracy of 97% is typically only observed in same model localization scenarios like 2D to 2D or 3D to 3D. Our method nearly reaches this accuracy despite being a cross-modal method, as you can see through these yellow and circles in the graph as well as the table here. Here we show qualitative results for 2D to 3D localization. You can see that the predicted 3D point cloud looks quite similar to the ground truth in all the cases. Now we discuss about 3D to 2D cross-modal localization. Our method beats the baseline by even bigger margin, almost 40% for recall at 1. It's important to note the stability of our performance across different modalities. While the baseline method shows a 15% reduction in accuracy when transitioning from 3D to 2D compared to 2D to 3D, our method maintains nearly consistent performance, further demonstrating its adaptability. Do note that the zero-shot LIP-Loc row, that is the last row here, where we achieved these results without even training on the KT-HD dataset. Our method significantly outperforms the baseline even when tested in a zero-shot setting. We discuss this in the upcoming slides. Here is the qualitative results for 3D to 2D localization. As you can see, the retrieved 2D image looks quite similar to the ground truth image. We trained zero-shot LIP-Loc on the KT dataset and evaluated it on KT3HD. Note that these results are without doing any customization of hyperparameter or using validation sets. As described before, our method beats the SOTA by 8%. This showcases our model's remarkable ability to generalize across different datasets and camera modalities. Here you can see that as we scale up the training on original KT dataset, the accuracy on TXT progressively improves. Here we show the diversity of KT60 dataset. Top row shows downtown with cars and houses, whereas bottom row represents highway with more greenery and wider roads. Our zero-shot model works well in all of these diverse settings. This marks the end of our presentation. Thank you for your time.